Okay, we're doing section 5, which is limit at infinity. So the limits at infinity is pretty much just talking about what the end behavior of the function is, so as we approach infinity or negative infinity. Graphically, if we were to graph this function, for example, 3x squared over x squared plus 1, function would look something like that. So obviously both ways the function is leveling off somewhere, and that place is at y equals 3. So what we could say is that f of x approaches 3, so that's the y value, our function approaches 3 as x approaches infinity. And then on the other side we could say f of x also, it's still positive 3 as x approaches negative infinity on this side. So that's what the graph would look like when we're talking about end behavior or infinite limits. And then numerically we would make a table, x values, put them into our function. We have to kind of guess what's happening at negative infinity as we get bigger numbers. Negative 100, negative 10, negative 1, 0, and then the same thing in the positive direction. So the negative infinity, we're just kind of guessing at. Let's start at 0 and work in the negative direction. So 0, 0, 1.5 for negative 1, negative 10 gives us 2.97, negative 100 gives us 2.9997. And as you go bigger, you could do 10,000 or something, and it's very, very, very close to 3. So we are approaching 3 as we approach negative infinity. And then it's going to be actually the same exact numbers going in the positive direction. 1.5, 2.97, 2.9997, and then we are clearly approaching 3 as we get to negative infinity. So the way we would say this in terms of limits is our limit as x approaches infinity of f of x is equal to 3, and the limit as x approaches negative infinity of our function is also 3. Here we talk about some horizontal asymptotes. The line y equals L is a horizontal asymptote if the infinite limits at negative infinity or positive infinity are equal to that number. So the reason we're talking about that now is because that's clearly what happened in our example up here. If you look at the blue graph, although poorly drawn, as we approach negative infinity and positive infinity, it levels off at some number. And we found out numerically that that number was 3. So 3 is a horizontal asymptote of this function. Okay, if r is a positive rational number and c is any real number, then if we have some function c over x to the r, the limit as we approach infinity is 0, or negative infinity is also 0. Okay, so this one we can kind of piece apart. We take each individual term, and we can add and subtract their limits. The limit as x approaches infinity for 5, that's just a horizontal line at 5, so that's going to be 5 forever, so this is what that limit is. And then this fits the definition from up above. When we have a constant over x to some exponent, that's going to give you 0. So the limit of this whole thing is just 5. Okay, now we have the limit as x approaches infinity of 2x minus 1 over x plus 1. If we plugged in infinity, virtually plugging in infinity at each of these, the limit of the top as we go to infinity is infinity, and the limit as we approach infinity of the bottom is also infinity. So it's not going to work to just plug it in or do anything we just did up above because it doesn't match that pattern. So what we have to do, it's a little trick, we're going to divide the whole thing, top and the bottom, by x. So we have the limit as x approaches infinity of 2x minus 1 divided by x over x plus 1 over x. Simplify. 2 minus 1 over x over 1 plus 1 over x. And now we can do what we just did up above. We can piece each part of this, take the limit as x approaches infinity of 2, which is just going to be 2. The limit as x approaches infinity of 1 over x, which fits our definition of above, so that's 0. The limit as x approaches infinity of 1 is just 1, and the last one is also 0, so our limit is 2. Okay, so we have three pretty similar looking rational functions. Each one on top, the x value, the exponent gets a little bit bigger every time. So what we're going to do is we're going to divide by x squared every time. The reason in the last one we divided by x is so we didn't get, let's go back and look at that one. We divided by x, we're usually looking at the highest power at the bottom. So let's go ahead and we need to divide everything in this by x squared. Okay, 2x plus 5 over x squared over 3x squared plus 1 over x squared. When you simplify that, we'll get the limit as x approaches infinity of 2 over x plus 5 over x squared over 3 plus 1 over x squared. And then we can take the limit of each individual term, since it's all addition at this point, put it in the top, 2 over x, that fits our last definition, that's 0, plus 0 over 3 plus 0. So that's 0 over 3. The limit for the first one is just 0. We're going to do the same thing on this one. We're going to divide by x squared. Notice the exponent on top is getting bigger. Divide it out, we get the limit as x approaches infinity of 2 plus 5 over x squared over 3 plus 1 over x squared. Take the limit of each individual term, 2 plus 0 over 3 plus 0, which is 2/3. And then the third one, the exponent on top has gotten bigger one more time. We're going to do the same thing, divide by x squared, because we can't have a 0 on the bottom, which is why we look at the exponent at the bottom. So we're going to have 2x cubed plus 5 over x squared 2x plus 5 over x squared over 3 plus 1 over x squared. The limit as we approach infinity of 2x, that's a line, and it's going to continue up to infinity. So on top, we really conceptually have infinity, and on the bottom, we have 3. So that limit does not exist. So this rule will pretty much explain what just happened. This is the same as guidelines for finding horizontal asymptotes. If the degree on top is less than the degree at the bottom, the limit is 0. If the degree is equal to, then we find the leading coefficients and we divide by the ratio, and that's our horizontal tangent or limit at infinity. And if the degree on top is bigger, then the limit does not exist. Okay, so now we have a new function, 3x minus 2 over the square root of 2x squared plus 1. We're going to divide by x. The reason we're dividing by x is because we're looking at the exponent of the biggest term, which is the square root of 2x squared, which is x. So we're going to divide by x. Okay, on top we get 3 minus 2 over x. And like I was explaining, we divide by x because this is the same thing as the square root of x squared. So we're actually going to make that into a square root and put it inside here. When we do that, the square root can simplify. Okay, then we can take the derivative of each, the limit, I'm sorry, at each individual term. On top, the limit at 3 is 3, limit at 2 over x is 0. And then on the bottom, we have the limit at square root of 2, and the limit of the square root of 1 over x squared is 0. Okay, so we have 3 over square root of 2 as our limit. So that was at positive infinity for the limit. This one is the limit as we approach negative infinity. So this time we need to divide by x, and this time our x is going to be negative x squared because we're approaching negative infinity. So on top it's just x. On the bottom is where we have to be concerned with the negative square root of x squared. So I'm going to put it inside right away, the exponent. And the negative stays out front. 3 minus 2 over x when we simplify, negative square root of 2 plus 1 over x, and then we put in take the limit at each individual point, and on top we get 3 minus 0 over negative square root of 2 plus 0, which is negative 3 over square root of 2. So the difference is you need to be really careful when you're approaching negative infinity versus positive when you do a trick like that. Okay, find each limit. Sin x, we know what that looks like. We're talking about what happens at infinity, so that same pattern is going to continue. So the limit does not exist because our function oscillates between negative 1 and 1. So that's one of those reasons why a limit doesn't exist. And then sine of x over x, roughly drawn. This limit is 0. And you could tell that from the graph when you look at the infinite behavior, the end behavior. Okay, now we have oxygen level in a pond. Suppose that f of t measures the level of oxygen in the pond, where f of t is 1 is the normal level, and the time t is measured in weeks. When t is 0, the organic waste is dumped into the pond, and the waste material oxidizes. The level of oxygen is measured by the function. So the question that we did not have written down yet is what percent of the normal level exists after 1 week, 2 weeks, 10 weeks, and then as we approach infinity. So we have a few different questions in here. Essentially what you're going to do is for the first 3, 1 week, 2 week, and 10 weeks, you are going to plug in, since the function represents the deterioration of the normal level, we're going to just plug in those numbers. This is 1/2, which is 50% of the normal level. And just plug in 2. This is 3/5, which is 60% of the normal level. Plug in 10 next. Which is approximately 90.1%. And then we also have to do, as we approach infinity, which is a little bit different, we need to divide everything by t squared when we're trying to take the limit of that. Minus t divided by t squared. T squared plus 1 divided by t squared. And then we can plug in our infinite limits at each of those. So we have 1 minus 0 plus 0 over 1 plus 0, which is 1. When we're talking about percents, it's the same thing as 100%. So it's back to approaching 100% normal level. If f is defined in an interval from a to infinity, the statement as the limit as x approaches infinity, f of x equals infinity, means that for each positive number m, there's a corresponding number n that's greater than 0, such that f of x is greater than m whenever x is greater than n. So really, that's extremely confusing, so we should just go on to the examples, which I think will explain the definitions. So if we're taking the limit as x approaches infinity of x cubed, because we know that x cubed increases without bound, then we know that the limit of x approaches infinity of that function is infinity, in fact. And then negative infinity, if we're thinking about the end behavior of that graph, it decreases without bound in the negative infinity direction, so the limit as x approaches negative infinity of x cubed is indeed negative infinity. And you're going to know that just from end behavior knowledge. Okay, find these limits. So we need to do polynomial long division to simplify this function. When you do, we're going to skip that part. We get 2x minus 6 plus 6 over x plus 1. And 2x minus 6 for sure turns into infinity when you take the infinite limit of it. So we know that this limit in general is going to be infinity. Same thing on this one, we have the same question, so it's still polynomial long division, get the same answer. And then when we think about 2x minus 6 in the infinite direction, in the positive, it's obviously increasing, and in the negative direction, it's decreasing. So we know this is going to be negative infinity. All right, now that's section 3.5 on infinite limits, horizontal asymptotes.